All right, so first up we have Matt. He is from Apple, talking about DataFusion. Give him a round of applause.
Hey everyone, I'm really excited to be here. One, just because it's been really amazing to see this community grow over the last 6 months or so, and I get to benefit from that with this fantastic audience that we have here. So what I'm going to be talking about today is a little bit of the symbiotic relationship between the academic communities, the open source communities, through the lens of projects that I contribute to, both free time and through my job. I have two requests. When I talk about database systems, I get very excited and I start talking really quickly. So if I stop making sense, tell me to slow down. The other is we have a super diverse audience here in terms of backgrounds and sort of context that you're bringing to the table. So if I say a term that you're not familiar with, stop me. Tell me to define something, and I'll be happy to do that. So with that, very briefly, I'll talk about why this topic is near and dear to me, a little bit about myself, and then we'll move on. I love database systems. As far as I'm concerned, they're the most important application in all of software. Every important application has a database underneath. They have a wonderful intersection of all these different sorts of problems like AI and theory when it comes to query optimization, programming languages when it comes to code generation and debugging, and of course like low-level systems performance issues when you're talking about query execution and storage design. I got my PhD from CMU last year. My research was on database systems and operating system interactions and how we can do co-design for those through a technology called eBPF. If that's familiar to you, if it sounds cool, let's talk after this. And now I work at Apple working on analytical distributed database systems. So a little bit of a shift for me from what my research was in. And that's probably the last it's not the last time I'll say Apple, but this is not an Apple talk, I guess I should say. That's enough about me, so let's dive into Apache DataFusion. And one piece of feedback I got when I gave this talk before was, when I was trying to describe what DataFusion is and what you can do with it, it's better to just give a demo. So I'm going to try to do a live demo very quickly, and we'll see how that goes, because it's not always great. So let's say you're an application developer, and you've got a bunch of, let's say, Parquet files or CSV files. You've got data, and you want to query that data. I'm going to make this bigger. I've got a Parquet file there. Cool. So what I'm going to show you very briefly is DataFusion has a command line interface. So people may have mixed opinions on this, but let's do some SQL. Let's say I want to see everything that's in this Parquet file from my application, and I don't want to have to write all the code. OK, there's a bunch of nulls. That's not helpful. Let's actually look at a couple of columns and see what's there. And let's throw a filter on another column. OK, we have 5,000 rows, which only showed the first 40. Let me add a order by and a limit clause, just because I want to see less data. But again, I want to be able to do this in my application without writing all the code to do that from scratch. That's what DataFusion is. It's an embeddable analytical data system. And so that's all for live demo. That's all I needed from DataFusion today. And we'll go back to the presentation if I can find my cursor. And so in figure form, let's say I've got all these queries. I can represent those as SQL. I can represent them with a data frame interface, if that's more familiar to people. And I have data at rest, things like Parquet, CSV. It can be Iceberg, just data that I want to be able to give some information about. I can feed that into DataFusion. And then the output that I get are my query results in the form of Apache Arrow. Apache Arrow is just a standardized in-memory format for columnar data. So it's a very useful format to store data in when you're passing it between different applications. So then you can take that data and then bring it into your super cool application. And you didn't have to write all the operators to parse the Parquet, to do the filters, to do joins if you want to join different tables together. All the SQL support is there that you want. So what is DataFusion actually providing for you? So once again, we've got user queries. We've got data at rest. DataFusion provides a lot of the guts that you would need for a database system. So on the front end, we have things like a SQL parser, different optimizers. I don't have time to go into the difference between a logical optimizer and a physical optimizer, but they're doing different things that are ultimately going to turn SQL into a query plan that the execution engine can then execute. And then there's some buzzwordy stuff like asynchronous I/O and vectorized operators. And what that means, it's just tuned to work on columnar data, typically analytical workloads, and generate really good performance. And then in-process execution, basically this is a library that you link against your application. So you don't have to go over an IPC necessarily to talk to DataFusion. It's actually embedded in your application. You just call it like a library. And then again, the results you get out are Apache Arrow. So a brief overview of DataFusion. It actually began as open source. It was created by my friend Andy Grove, who works with me at Apple. And it was donated to the Apache Arrow as a sub-project, and it's now a top-level Apache project. The GitHub repository is pretty active. There's hundreds of contributors and almost 10,000 commits. And DataFusion actually reached a state where we were thrilled with the performance as a community and the stability to submit a paper to SIGMOD last year, an industry paper. And there's a couple more folks from my team at Apple on the author list there. And that kind of goes into some of the details about what you can do with DataFusion and how it stacks up to sort of the other state-of-the-art systems right now. So what are people doing with DataFusion? Like, why does this exist? There was this observation that whether it's Databricks, whether it's Snowflake, whether it's BigQuery, whether it's Redshift, there's a lot of companies spending a lot of time building bespoke columnar query engines, when in practice, they're doing a lot of the same things. So one thing you can use DataFusion for is to build new database systems like I described. So there's a lot of examples of startups out there like InfluxDB, ParadeDB, GrepTimeDB, as well as a lot of companies using it internally that they don't like to talk publicly as much about, that are building database systems around DataFusion. And the interesting thing here is the database community really likes to bin systems into like, oh, you're a time series database, you're a graph database, you're an analytical database, you're an operational database. There are people building all kinds of database systems on top of DataFusion because it's this sort of extensible, pluggable, embeddable query engine. This is a little bit of foreshadowing for the work that I'll talk about shortly. You can also use it as a query accelerator for existing database systems. So instead of building an entire database system around DataFusion, you take an existing database system, rip out its query engine, and drop in DataFusion instead. So we'll talk a little bit more about that in a few slides. A lot of folks are using it. I showed you the CLI very briefly. It's a nice scriptable interface. It takes SQL. So a lot of folks are using just the DataFusion CLI to do like batch ETL jobs, data compaction, data transformations, often to switch between formats. Like if you're changing Parquet to some other format, there's Vortex and LanceDB are sort of newer data formats, but Parquet and Iceberg and Delta are sort of fighting for like to become the standard for analytical data lake formats. And then another sort of emerging area is providing things like Python bindings for Jupyter notebooks, which are traditionally used more with ML workloads. So that's something that we're seeing a lot more questions pop up on, like, how do I use the Python bindings to do things like training an ML model? So is DataFusion fast? This is one thing that we care about as database designers. This is actually from a blog post in November on the ClickBench workload, single node, partition Parquet files. DataFusion was the fastest. Take that DuckDB, but actually this is out of date. DuckDB has since leapfrogged us again, but it's great motivation for us to keep going at it. No, we love the DuckDB guys. It's like wonderful to have competition in this space. And what I want to highlight here is performance remains like something extremely important to us. Like we always want to be making improvements with major releases. That performance is improving over time. We want the system to become not only more reliable, but also faster.
I have one question.
Sure.
So all of those are relative time? Just out of curiosity, what is it relative to? Like they're 1.06 is the fastest. Relative to what? What's 1.0?
I want to say, that's a wonderful question. I'd actually have to check that link, which we can do after. I will make sure these slides are available, all these links work, and I'll double check what this is relative to. I don't think it's ClickHouse. I'd have to double check.
And I bet not, given they're at 1.75 at the bottom there.
Right, yeah. So one of the ways, like particularly when we talk about performance over time, one of the things I want to highlight is one of the ways we got this performance improvement in DataFusion. And that's something called German-style strings, which maybe sounds weird. Maybe you've heard of them before, but we're going to learn about them right now. And what I hope you take away from this is that data representations matter to performance. We don't always think about what happens when you type standard string in C++ or any other, pick your language of choice, when you define a string object. German-style strings are implemented in DataFusion as something called StringView. And for DataFusion, the benefits here are that we get faster loading of Parquet files and faster filtering of values. I'm going to show you how that happens with German-style strings. Why are they called German-style strings? That was because of the research group that sort of popularized this approach. The Germans at TU Munich built two extremely successful research platforms, one called Hyper that they sold to Tableau, which was later acquired by Salesforce, and then their current system is Umbra. It's commercialized as CedarDB, and these are just like a smattering of some of the most interesting papers to me. They've had dozens of papers built on these systems. Really just foundational work over the last 15 years in high-performance analytical database systems, and just really amazing people, too. I'm very jealous of them. So before I describe to you what a German-style string is, let's talk about what strings look like right now in maybe some languages you've used or still use. So let's start with C. OK, it's an array with a null character at the end. That's about it. It's pretty much always going to be allocated on the heap. You're going to have to chase a pointer to read this thing. In C++, a standard string is going to have this whole mess of data, 192 bits. But the problem is you're still always going to chase a pointer to get to the actual data that you want to check. And this is a problem because in database systems, we're typically doing filters on strings, or we're doing some sort of check on a subset of the characters, or like an aggregation on these strings. So if we want to do anything useful, we're going to chase an extra pointer, which in architecture land means the data we want to look at isn't in the CPU register. We have to load the pointer, chase something else in memory. It's a mess. It's super slow. We don't want to do that when we're processing billions of values at a time. This stuff matters. So motivated by the state of the art, or the state of the world with how pointers or strings were typically represented, there were a few observations about analytical workloads. One is that most strings are actually quite short, whether they're things like the state you reside in, or the city. I mean, I'm doing address, but like names, things like that. They're typically quite short. It's not like an entire novel in one string field of a database system. And another is that strings are pretty much immutable. Even if you move once a year, you're not changing those strings very often. So in an average data set, strings are fairly fixed. And another is that we're usually only looking at a subset of the string. We're looking at things that they begin with. We're trying to order them. So we're also only looking at the prefix of the string. So the proposal was, let's try something different with strings. And so instead of this C++ string that has 192 bits on the stack that you still have to chase a pointer, we ended up with this representation where you have 128 bits. And in a short string, you just get the length at the beginning and then the content. You can embed it. This thing can live on the stack. Most modern CPUs actually have registers wider than 64 bits, so this is great. You can chew through these things like crazy. You don't have to chase an extra pointer. You can do all the operations you need in a very short amount of time. And for a long string, that 128 bits on the left actually changes from the length and then 4 bytes of prefix and then the pointer to the actual on-heap full string representation. And the beautiful thing about this representation is you can often do a lot of the work that you want just by looking at the prefix. You never actually have to chase the pointer, go over to the heap, and look at the full string representation. So this data layout actually improves performance dramatically with reducing pointer chases quite a bit. So if you don't believe me, well, go read the Germans' papers. They love it. But someone actually, yeah.
The German style, because it's TU Munich.
Yeah. Yeah. My advisor, Andy, seems to have popularized that term in his lectures.
Pablo?
Yeah. So someone said, OK, well, let's implement this in DataFusion. Let's take this research idea, because the reality is research, having seen how it's done, like you can pick your workloads to make your research look really good. So maybe it's the case that this doesn't generalize to other systems. So someone said, let me take German style strings and implement it in DataFusion. And that was a project someone did last summer. And we ran the ClickBench workload. And there's 42 different queries. And a lot of them have no improvement, right? Because maybe they weren't doing anything with strings. But if you look at query 10, over a 2x improvement. So there is a real performance win. It only averages to about an 8% improvement in ClickBench, but certain queries benefit greatly from this. Now, obviously, there is a downside with that string representation. If your strings are just state abbreviations, 2 characters, right? You're still going to pay 128 bits for every single string. So there is a little bit of memory overhead that you're going to pay for this representation. In practice, if data's at rest, you can do things like compression to fix that problem. But in memory, you're going to pay some overhead for that. You can do other tricks. Yeah.
So going back to that previous example, why is the long strings pointer 62 bits long?
Yeah, so thank you for asking that. The Germans they love doing this, but this is actually something quite common in database systems where you only need 48 bits for a pointer. At least you only needed 48 bits until very recently. There's only 4-level paging in a page table in an operating system. The other high bits, 16 bits on an x86 64 system, you could do whatever you want with it. You could stash stuff in those bits. You could use that data for whatever terrible things you wanted to do. Now there's 5-level paging, I think, in the recent Linux kernel, so there's only 57 bits, or there's 57 bits in use now, so you have 7 left to play with. Yeah, you're technically not supposed to do that, but as long as you, mask off the bits before you dereference it, who's gonna know? But someday, if pointers are actually 64 bits, then this approach, that specifically where they're stealing a couple bits to represent something in there, that won't work. Yeah.
Can you avoid the conditions?
Can you? Well, sure. Yeah. So you could basically templatize different kernels to do the filters, and if you know a priori that often when you're reading a Parquet file, you know what the longest length of the strings in a given column are. So you could immediately call into the kernel that only does the short string filters, so you never even have the extra branch. Absolutely. And in fact, I link here to the CedarDB blog post. They say why German strings are everywhere. They actually just did a recent post talking about branching and stuff like that and tricks that they do to call into when they know something about the data a priori, they can use a function that doesn't have the branch and just kind of rip right through it. So like I said, I'll make sure slides are available and people can find them.
Am I understanding right that if you're just looking at the first 4 characters, it's actually the same in either representation?
What was the last part?
If you're looking at the first 4 characters, it's actually the same in either representation. Index it?
Yeah, absolutely. Yeah, if you never need to look past the first 4 characters, you don't actually need to know whether it's a short string or a long string. Absolutely. So if you have a begins with, you could potentially never really need to have many branches at all and just rip right through. Yeah.
Is that also the reason the length is 32 bits even in the short case?
So the question is that the reason? Sorry, I've been bad at repeating questions. The question is that why the length is 32 bits in both the short and the long case? I believe so, yes, because then you always know where the prefix is always beginning at the same point, so you can jump to the same offset every single time to read the beginning of the string. So, okay, I did this. All right, let's talk about Comet. This is the one that's really exciting to me. So if you think I'm pumped now. So before I talk about DataFusion Comet, I need to talk about Apache Spark, another Apache project. So Apache Spark so Apache Spark actually began as a research project at Berkeley, out of AmpLab. Apache Spark is used for large-scale distributed query processing. It's sort of a response to the MapReduce era of, I don't know how many people, some people know what MapReduce is here, some people don't. We're coming up on probably 15, 20 years old of MapReduce. But anyway, it was a response to that processing model. I think I mentioned it came out of Berkeley's AmpLab. And it eventually led to the Databricks startup that just, I think, had a $15 billion Series J a few weeks ago, whatever it is. Anyway, so there's some downsides to Spark, but it is widely used in industry. Some downsides, it uses row-based query processing, and what I mean by that is if you have a table with 3 columns, A, B, C, and you have a filter on A, what you'd love to do is just rip down A and just do the filter immediately. But because it's row-based, it's going to materialize. It's going to copy the 3 fields for a given row, A, B, and C, look at A, and then say, OK, discard this. And then it's going to process row at a time. So that's not ideal in an analytical system where you just want to be able to rip down A and do the filter that you want and then materialize the subset that you need to. As was the style at the time, it was written in Scala, so it runs on the JVM, so it's not going to be as fast as native code. And as with any JVM application, there's a garbage collector sitting there that could add unpredictable latency. There's ways to tune the JVM, but it's going to kind of get in your way. Which brings me to DataFusion. Oh, no, we're still talking about Spark, sorry. So what does Spark execution actually look like? So there's a driver that sort of coordinates everything. It's typically attached to an application. It hands off a Spark job. You can use SQL to express your work in Spark, and your data can be at rest in Parquet files, similar to what I was describing before in DataFusion. But the scale we're talking about here is thousands of systems, petabyte scale operations. The scheduler then hands off tasks of this query to individual workers. So this is where you get the fan out into thousands of systems. Every worker represents like a virtualized server possibly, or an actual physical server. And then within that, there are executors that actually run your job. So there's further parallelism across CPU cores, typically 1 executor per CPU core per worker. So that brings me to Comet. So I alluded to earlier this idea of you can use DataFusion as an accelerator for an existing database system. So that's exactly what DataFusion Comet is. It's an accelerator for Apache Spark based on DataFusion. We can accelerate things like Spark shuffle operations, which I don't have time to go into, things like data loading I described earlier, reading Parquet, operators like joins and aggregations, expressions, so different filters and things like that, and then functions like, let's say you wanted to know the standard deviation on a numeric column or something like that. We can do that in DataFusion as well. And if there are unsupported operations, we can fall back to Spark seamlessly. So you can get some sort of hybrid execution if part of your query plan we can't actually run natively on DataFusion just yet. And it may be the case that there's nothing preventing us from running it there. It's just we haven't implemented it yet.
I know you didn't want to go there, but how does a library accelerate shuffle, which is the
so Spark
passing data between your executors?
Spark has a pluggable shuffle interface. So there's a couple third-party shuffles. I think there's ExaShuffle, which is more of a research project, but there's a couple others. But because the interface, Celeborn is another one. Spark Shuffle is sort of pluggable, so we can write something that basically speaks that API. Compatible with Spark 3, 3.4, 3.5. We have experimental support for 4, which I think is in release candidate any day now. Spark 4 should be out very soon. And it was donated to the Apache Software Foundation in February 2024. So where does Comet actually fit into the picture for Spark execution? So you've got the driver still, and you've got Spark. But once Spark generates the query plan, Comet steps in and says, OK, I see all the operators you've generated, your joins and your scans. I'm going to replace those with DataFusion operators. It still goes to the scheduler. It still goes to Spark workers. But then when you get to the executor, we also have DataFusion sitting there as a library, and it receives those DataFusion query plans, executes, in theory, the same query faster than Spark can do it, and then hands the results back to the Spark user as if they were just, because they are speaking directly to Spark. It's just the query engine was able to execute the query much faster. This is not a totally new idea. So I alluded to Databricks earlier, which I'm selling them a little short here. They do a lot more than this now, but they started as basically Spark as a service 15 years ago now. Maybe plus or minus a few years. But they had the same idea. They said, you know what, Spark's really slow. We're going to build a native query engine for Spark. And they called it Photon, and they published an awesome paper about it. And it's also an Apache Spark accelerator for their Databricks product, which is built on Spark. And it uses a vectorized C++ engine. And one thing I really, really like about this paper is, and it's kind of unusual for an industry paper, is they discuss a lot of the design trade-offs. And what I mean by that is most papers that are industry papers get up there and say, we did X, Y, and Z, and they worked great. And we're not going to tell you what other stuff we looked at. They actually discuss a lot of trade-offs between whether they should compile queries or interpret queries. They looked at like, okay, if you're running a filter over a bunch of data, and you filter out some rows, is it better to represent that with a bitmap or an offset vector? And then when do you compact that? Like they actually talk about some of the design trade-offs and how they ended up going down the paths that they chose, which is one of the reasons it's a great paper. And I don't want to reduce DataFusion Comet to we're re-implementing this, but there's a lot of wonderful ideas here that we can look at and then apply those to DataFusion Comet. So what are some of the challenges? I mean, this is a very testing-heavy crowd usually. So particularly with something like Comet, what are the challenges with something like this? One is that Spark is a moving target. I mentioned we target support for Spark 3.3, 3.4, 3.5, and upcoming 4.0, but behavior changes between major Spark releases. And so there's different knob configurations that you can change in Spark that may change the actual query results. For example, things like configurations can change casting behavior, or like how does Spark behave when you do overflow on integer addition. So like Spark 4 is going to introduce ANSI SQL, which is going to be, I think, meaning that if it overflows, it generates a null, but current behavior doesn't generate a null, it lets it overflow. So we have to match that behavior in Comet if we want to provide the same results that Spark is currently producing. So we don't have to intentionally introduce bugs into our system, but we're sort of intentionally introducing bugs into the system. There's data representation differences. So like Spark uses Java big decimal and Arrow uses decimal 128, and that's just sort of a type difference. But like Spark doesn't speak unsigned types when you use unsigned types in SQL. It just promotes, like if you have a uint8, 1 byte, it promotes it to a signed 2 byte, like an int 16. And when you do addition on those types, it does weird things, and we have to try to support that. Performance, I love talking about performance. So all those quirks aside, all those challenges, does Comet actually work? So in this, we're running TPCH. On the y-axis, I'm showing elapsed time for this entire workload. And on the left, we have Spark 3.4.3, and it takes about 10 minutes. This is, I think, scale factor 100, so about 100 gigabyte data set, single node. This is not single node. This is a couple workers, but this isn't a massively distributed system like I described before. This isn't like 1,000 workers or anything like that. But it takes about 10 minutes, and with Comet there, we can roughly have the time. It's not quite a 2x improvement, but it's really, really close. So it works. So where are we going next with Comet? One, we need better fuzz testing. Our testing is I don't want to say anything too deprecating, but you can never have enough testing, right? Like we need better testing. And like I said, it's really hard with Spark as a moving target to make sure we're not only not generating bugs in our system, but we're adhering to Spark behavior across versions. We're adding complex type support. So what that means is things like arrays, structs, and maps embedded in people's data types. This is becoming increasingly common. We need to be able to support that in things like in Comet. So right now, we have our own implementation of a scan. If you're reading a Parquet file, we have a Comet scan operator, but it doesn't support complex types. So we're extending the system to use DataFusion's Parquet reader, which already has complex type support. But then we're going to have to go in and add all the functions and expressions that you can do to complex types. And then the last thing is, we want to go back to the German-style strings and try to implement those in Comet. It should be pretty easy. We're using a recent enough DataFusion version that we should be able to get the benefit of using German-style strings when we're loading Parquet files and doing operations on them and get that free 8% and ClickBench, whatever it was, get all those performance wins. But we have to do all the extra work of Spark Shuffle now needs to support string views. We now need to be able to convert string views back to the native Spark types when we output the results. So there's work. It's not just flipping a flag and we get free performance wins, but it's what we want to do next. So what I want to hammer home in the last couple minutes is, how do you get involved? Like, you're excited. DataFusion sounds great. DataFusion Comet sounds great. You either want to start using DataFusion instead of DuckDB, or you want to like learn about database systems in general, because a lot of the things I've talked about sound really cool. So first, how to get involved. The open source communities. These are the 3 GitHub repos I stare at the most. There's DataFusion, there's DataFusion Comet, and then there's ArrowRS. I didn't mention, these are effectively all Rust code bases. So if you want to learn Rust, here's a great way to do it. It's a fantastic community. I didn't really know Rust 6 months ago, and here I am. It's a fantastic community. There's a weekly DataFusion community meeting every Wednesday at 11 a.m. Eastern. It's on Google Meet. It's not just people working on DataFusion and Comet and ArrowRS. It's a lot of people trying to figure out how to use it and how to use it to solve problems. And so if you look at DataFusion, you have a question, you say, how would I do X, Y, or Z? It's a fantastic resource to kind of, it's almost like office hours for whatever people want to bring to the table. It's a great resource. And then the last is there's an Apache Software Foundation Slack. That one requires an invite, but if you want in, just poke me or something. We'll find a way to get you in there. We'll kick the door down. So if you want to learn about database systems, this is Andy Pavlo. He was my research advisor. All of his resources are available on the internet. So his intro database systems class. His advanced databases, that's a graduate level class. He does special topics classes. He's doing one right now on query optimizers. There was a previous one on self-driving database systems, which basically means machine learning for database systems. How do you make database systems run more efficiently, automatically? There's a YouTube channel where he posts all of his lectures as well as all the seminars that he runs. So last night we had the Germans that I was describing 20 slides ago giving a talk about how they want to destroy SQL and what they're proposing to replace that. So that should be on YouTube probably today. It's usually the next day. But you can also join those seminars live on Zoom if you want to ask those sorts of people questions. Yeah, lectures, seminars, sure. There's also just a general online systems community. So Discord, there's a software internals Discord, which is awesome. I mostly hang out in the DBs and the papers one, but there's a lot of different ones for like people that are interested in networking, you name it, system stuff. There's a DataFusion/ArrowRust Discord, and then there's the DC Systems Discord. There aren't a lot of people in there right now. Like, let's get that up. Let's talk about it. And like, please tell us about more. Like, I'm sure there are other fantastic communities out there that are doing cool systems work. Takeaways: database management systems, communities, everyone's awesome. DataFusion is awesome, high performance, embeddable analytics engine. And Comet is awesome and uses DataFusion to accelerate Spark. And please reach out to me if you want to chat about anything I talked about. Database systems, Andy Pavlo, spending 7 years with that guy. And yeah, that's what I got.
So we probably only have time for like maybe 1 or 2 questions, but if anyone has any.
Is there any resources comparing Photon with Comet?
So the question is, are there any resources comparing Photon with Comet? In theory, we might be able to run Comet. It's a little apples to oranges because I think the way Databricks provisions systems, I'm not totally sure we get an apples to apples comparison. We can only look at their paper, which 3 years ago already was saying they got a 3x improvement from TPCH. So we're behind, no question. But for a ragtag bunch of open source contributors, we're doing okay. But no, I don't have a direct Databricks comparison, like a Photon comparison for you.
Yeah, so you said that Spark is a moving target. So I was wondering if you do any specialized testing to make sure that all the changes in the latest version of Spark you catch in Comet?
So the question is, Spark's a moving target. Do we do any specialized testing, like say for example the 4.0 release to like look for regressions and stuff like that?
Yeah.
So right now, like Comet CI runs a bunch of different Spark versions. I don't think we've added the 4.0 preview yet to CI. We'll put it there, and we'll just kind of see how it goes, and then we'll kind of go through and have to see what's broken. Yeah, it'll be a lot of work.
Cool. That's all we got time for. Give Matt another round of applause.